The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading, interdisciplinary solutions to significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. These research areas broadly fall under three main themes, including advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation. Look into the factors and mechanisms influencing human health and wellness and develop evidence-based solutions, and generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good afternoon, ladies and gentlemen, colleagues and students. Welcome to this PAIR Distinguished Lecture Series. My name is Qingyan Chen. I am the Director of the PolyU Academy for Interdisciplinary Research, or PAIR. It's my great pleasure to introduce our distinguished speaker, Professor Vikram DESHPANDE today. He is a leading expert in solid mechanics and the professor of materials engineering at the University of Cambridge in the United Kingdom. From pioneering micro-architectured materials with exceptional thermal resistance and toughness to modeling the behaviors of the soft and active materials, Professor DESHPANDE's work has greatly advanced our understanding of complex phenomena in material science, ranging from plasticity, damage, and failures in the metal alloys to how living cells and tissues sense and respond to the mechanical forces. So his team has delivered both theoretical and practical innovations with a widely engineering impact. Among his most notable contribution to the development of metallic wood by engineering nickels into a porous nanoscale architecture resembling wood. He created a material as strong as titanium, yet 4 to 5 times lighter. So other extraordinary achievements include the inventing of new classes of architectural materials from lightweight structure, energy absorption, and shock mitigation, and developing theories and tools to improve the blast resistance of land and sea vehicles, and to evaluate the high temperature performance of alloys used in engines. So Professor Despande's engineering excellence has been recognized with some of the world's most prestigious honors, including awards from the American Society of Mechanical Engineers, the Society of Engineering Science, and the European Mechanics Society. He is also a fellow of the Royal Society, the UK Royal Academy of Engineering, and an international member of the US National Academy of Engineering. So without further ado, ladies and gentlemen, please join me in welcoming Professor Despande.
Thank you very much, Professor Yan. It's a great honor and a pleasure to be here and to give this lecture. Of course, what I'll be talking about today is not my work, but it's a work of a lot of my students and postdocs. Some of them I've named here, and I'll talk about them as I'll go along. But I'm talking to a broad audience, so I'll try to keep it sort of relatively broad to sort of say what is the main aims of what we are trying to do. And you can see that I've slightly changed my title, like you normally do as an academic, is what I'm going to be focusing on is not just to talk about these measurement strategies for data-driven mechanics, but actually what has come out of the work over the past few years is that as we've come up with these measurements, we have started to learn new physical insights. In some ways, that's more exciting to me than just sort of saying that we are doing measurements. And so that's what I will be focusing on is what are these physical insights as well. So of course, this work has been sponsored by lots of people. So I have to acknowledge them. Okay, so what is it that's really motivated all this to start off with? So this was a problem that came to us, and they said that there's this thing called a blisk. And what we mean by this thing called a blisk is this bladed disc, which is used in every aerospace engine, basically. And it's right now made out of a single metallic alloy. The question is, what can you sort of improve its performance by making it a multi-material system? I.e., you sort of continuously grade from one alloy to another alloy, because that's what's possible now with additive manufacturing. So that was the problem that sort of motivated all this work. So the idea is that we started with this Honeywell blisk, and I'm just going to give you a broad view of what is it that we were trying to do. I'm not going to be talking about all of this in this particular talk. And we wanted to take this titanium blisk and see, can we sort of reduce its weight, increase its working temperature, etc. And for that, of course, we said we'll have to make lots of different alloys. And now you can make lots of different alloys by some powder routes, lots of other routes. But now you'll have to measure the properties of lots of these alloys to be able to do this kind of optimization process. And so we'll have to do very few measurements. So we have to be, rather than doing lots and lots of measurements, we want to do very few measurements. So you make some complex specimen from which you can get lots of properties in one go, basically, rather than having to do different tests. We'll discuss this as we go along. And then you make these specimens, and then you come up with saying, how do you do these measurements on these very complex specimens? Because you're trying to get lots of properties from one specimen. And these are these different measurement strategies, essentially all X-ray kind of based, and that's going to be one of the main focuses of the talk. One of the things is because you're doing so many different alloys and so many different measurements, you want some autonomous way to get these measurements into some kind of a model that you'll be using. And this is where our data-driven ideas come in, that you don't actually come up and develop traditional models, but you have an autonomous framework. So that's approximately where these ideas of machine learning come in. You come up with an autonomous way from these measurements to go into a constitutive model. And these constitutive models finally will go into some kind of an optimization tool. And that's what you'll then close this loop to understand how you can develop this whole kind of come up with a multi-material design, basically, from alloy development to measurements to, of course, the final structural design. What I'm going to be talking about today is this element of it, which are these measurement strategies. Let's assume that we have got lots of these alloys. How will you actually come up with these kinds of measurement strategies? And that's where this whole idea started developing, is that how do we come up with different measurement strategies? Because the traditional measurement strategies are too labor-intensive, too slow, etc. Okay, so given this, now that that's the sort of broad focus, I may not come back to this problem in any great detail, but I'll focus on this real science that we're trying to do, which is the measurement of measurement strategies. And I'll discuss three methods. Two of them I'll discuss in a very sort of bird's eye view, and one of them where we will basically talk about these physical insights, we'll go a bit more in detail. So the measurement strategies are all laboratory-based. We do not want to go to synchrotrons because we want to do this fast, we want to do it cheaply. So they'll all be laboratory-based, so there'll be X-ray methods. We'll use diffraction. You'll see what kind of things we've had to do to bring some synchrotron technologies into a laboratory for these kinds of diffraction tests so that we can do many, many multi-axial measurements with one test, basically. We'll do high-speed tomography, so things where we'll be able to do tomography at millisecond timescales. Traditionally, tomography takes minutes to hours. And then finally, I'll also talk about doing three digital volume correlations. And this is where we will talk about real new physical insights that are coming in, things that we never expected that we'll be able to see. Okay, so let's first talk about trying to do lots of measurements from one specimen. So this is sort of, I'm giving it at a relatively bird's eye view. Okay, so the problem is that if you want to extract multi-axial constitutive models from metal alloy, it's a harder problem, as we know that it is full of internal sort of state variables or history variables, right? There's plastic strain, etc. So what has traditionally been done? So you're trying to do, this is a multi-axial curve. So you have lots of these different specimens. Oops, what did I do there? I need to learn how to use this. So they have lots of different specimens giving you lots of different stress states. And so typically to do this kind of measurement, you need to do 50-ish tests or something like that, which takes too long. An alternative method, which has been used now for the last 20, 25 years, maybe a bit more, is you design one sort of statically indeterminate specimen. So you have effectively lots of multi-axial states triggered in this one complex specimen. And when you do that, then you can sort of maybe extract out these multi-axial properties from one specimen. The problem here is that you only use what is called these DIC, which are optical measurements. You look at the specimen and you basically say, what are the strain fields? This is like PIV or something like that in fluid mechanics. The problem with that is that you now have measurements of the strain, and now you're trying to sort of extract what is the local stress at every point in this specimen, at every point here. And that's an inverse problem. And that inverse problem requires you to solve some kind of other thing, typically some kind of boundary value problem. And that's typically highly ill-posed because effectively you are not directly measuring the internal state variables. So the question is, what can you do because this is too ill-posed a problem, and hence you need to do still lots of different measurements. So the question is, we said to ourselves, can we develop something new? So this is the traditional technique. You're only doing optical measurements. And now these are these sort of ill-posed inverse problems. How can you regularize this ill-posed problem? Well, there's one thing you can do, is in addition to measuring these strains, suppose I actually measure the changes in the atomic spacing. Changes in the atomic spacing will then tell me the elastic strains, because that's what's actually generating the stress inside the materials, because the atomic bonds are being stretched. Now you can do that by effectively Bragg's law, which is this idea here, is that you have an incident beam, you have a diffracted beam, and basically looking at that diffracted beam, you'll be able to get hold of what is the atomic spacing. Now, in reality, what you do is you don't do it for a single crystal, but just like when you're doing a computation, you define some kind of a representative volume element, which is what we have got here, is that you want to know what is the average elastic strain over that representative volume element inside this material. And that's what we'll do. And what happens there is as you load this, is that the energy spectrum, by Bragg's law, will shift from this unloaded state to this loaded state, and that will give you the elastic strain. So now you've got yourself this rather interesting measurement tool, where if you do this kind of a test, you not only are going to be measuring these strains using something called digital image correlation or something like that, but you'll also be measuring the elastic strains. So the total strains as well as the elastic strains. That means you know the stress and you know the total strains. And that means that as you start loading the specimen, at every point within this specimen, so for example, this particular point here, you'll get a multi-axial stress-strain curve. At another point here, you'll get another multi-axial stress-strain curve, and another point here, you'll get another multi-axial stress-strain curve, with solving no inverse problem at all. So with one test, you're going to get lots of these different multi-axial stress-strain curves. And that's how you basically have reduced the problem to doing it in one measurement, basically. One test is going to give you all that data. So that's what we are basically saying here. And so this sort of, as a theory, is well known. It has been known for, at least 50, 60 years, if not more. The question is, how do you go about doing this in a lab? Because you need to be able to do these diffraction measurements. So this was the first thing, is we needed to build ourselves a laboratory facility to be able to do this. Now, what I'm going to show you is a movie in which I will show you the main aspects of this facility that we have built to do these kinds of measurements. And because these measurements have not been done in a laboratory before. Okay, so what you'll see are various different things in this movie. You'll see an X-ray source here, which consists of a metal jet, a liquid metal jet. This will be the loading apparatus, and here there will be detectors, and there will be some sort of X-ray optics sitting here. So let's just look at these various elements. So what you're seeing here is this is the X-ray source, this is the optics, this is the load frames. We are doing DIC as well, and these are the different detectors. So let's go into that X-ray source. That X-ray source comprises of a liquid metal jet, indium in this case, approximately 80 meters per second. An electron beam comes and hits this liquid metal jet. You get an X-ray, sort of X-rays emitted, but they are sort of in a conical shape. You have to collimate it. And then you get these collimated beams, they go into this specimen. They will hit this specimen, the X-rays will diffract from all these crystals, which are these crystal planes that you're seeing here. And they go into these detectors. These are very high efficiency detectors. They've been cooled to a very significant level to sort of reduce noise. And as you load this specimen, you have first this normal diffracted beam. As you load it, the spacing of the atoms changes and the energy spectrum moves. And that is essentially how you can then get hold of the elastic strains. And then you can get effectively all this data throughout this specimen. So that's this idea about this facility. And that's what it actually looks like, okay? It doesn't look as fancy as that movie, but that's what it actually looks like. So that's what we have done. And so this is what you can get. So for example, if we have this kind of a specimen here, which looks like this, which is just this kind of a notch specimen, at one point, I'm showing you, at this root of the notch, we're going to get these kinds of multi-axial stress-strain curves. And what I'm showing you here is the measurement, which is these black things, and two different models, classical plasticity models, the best possible classical plasticity model that we could come up with. It actually doesn't do that great a job in predicting the strain hardening behavior. And that is the yield surface that we are showing you here. This titanium doesn't behave like a typical we call in plasticity theory a von Mises material. And we've also developed what is called a recurrent neural operator model, which is a neural network model. And this is the comparison between the sort of experimental data that we have got here on the top row and the neural operator prediction of what that curve looks at. So we have effectively used only one specimen, a simple notch specimen, to calibrate the model. And then we have validated the model against this sort of rather more complex specimen. And this was this sort of autonomous framework. So going from one measurement to automatically generating a plasticity model without sort of any sort of real intervention. And to the best of our knowledge, this is the first time from real experimental data using a single specimen that this has been that this kind of a thing has been done. So this is sort of the one bird's eye view of the first aspect that I wanted to show, that you can actually sort of now develop these tools which are actually generating huge amounts of data. I mean, I didn't go on to tell you how much data is being generated, but one particular specimen is giving you plasticity data of many sort of, megabytes, I'll call it, but actually speaking, the information content is much higher than sort of being in terms of bytes. So the next thing is I'll talk about high-speed imaging, basically, in sort of 3D, or what I'm going to call 4D, because it's going to be 3 dimensions in space and 1 dimension in time. So the point is that now we are going beyond what can be done even in synchrotron. So let's say we have a battery problem, and let's talk of a thermal runaway in a battery, and you want to observe what's happened. Why did this battery suddenly fail? So this is synchrotron data, and this is what it looks like. So this is what's happening, and that's it. That's what you see. That's when the battery suddenly sort of gave up on you because you got a thermal runaway process. So these are radiographs. This is pure 2-dimensional imaging. It's very high speed because it's in a synchrotron, but it's 2-dimensional. It doesn't give you the information that you need to understand of how this 3-dimensional failure actually took place. Okay, so 2D visualization is sort of, it's useful, but it doesn't go that far. Now, what else can you do? Suppose we do a lab experiment. This is high speed. This is photography. So you compress this at a reasonably high rate. This experiment is finished in 4 seconds. Well, it was a softening curve, a much slower experiment, which went on for nearly 1 hour. There was sort of no softening. But actually, if you were closely observing that those sort of the optical imaging, what you observed in the optical imaging is that the deformation mode looked the same in both the cases. So the slow mode and the fast mode looks the same, but there must be something different because there was a softening that was occurring in the high rate deformation, and that slow rate deformation was not giving you the softening. So, but the 2D imaging, which is essentially optical imaging, did not tell us what is the difference. Well, if you look at the specimens in an X-ray image after the whole thing was finished, what you'll see, there was a crush band that formed in the high rate experiment. And that softening must have been due to that crush band. But what we did not get, because we only imaged it after the event, is we could not actually observe how that crush band formed and evolved over time, basically. Okay, so why is it that we cannot visualize this in real time, basically? What is the problem in not being able to visualize in real time? How does tomography work, right? Why is it so difficult to do it? Is effectively what you do is you in tomography, you take a specimen and you rotate that specimen, and you rotate it over sort of many orientations, typically 1,000 or more. And you'll have 1,000 or more or so orientations, and you use 2-dimensional images, and then you sort of reconstruct the 3-dimensional thing over that. So the key here is that you need to do these. You need to take many such images over lots of different orientations, and that's what basically makes it very difficult to do it in high speed. So the question is, can we do this in a laboratory much faster? Can we do this very fast, i.e. not having to rotate it over 1,000 orientations? And then can we basically do high-speed tomography? So the idea here is rather simple. Of course, the implementation is much more difficult. And let's just see what I'm going to show you here. This is the real experiment we did in the lab. We were deforming this specimen. And what was happening here is that, and we are rotating it at the same time. At each instant in time, we did not actually capture the 1,000 orientations you need to do a full reconstruction, but rather at each time we captured one projection at different orientations. So the only data we have is that we have one projection at different orientations at every instant in time. So this is extremely sparse data, but can we use this very sparse data to do a full 3D 3D or 4D reconstruction in space and time from such a sparse data set. Well, at this point, we can again now bring in physics, really. And we can bring in physics to see how is it that we can do this reconstruction. And the reconstruction is going to be based upon two basic ideas. One is something called neural radiance, which is sort of an image, one of these AI-based image processing ideas. But let's not discuss that in great detail here. The key point is that we have two static images. We have images at the beginning and the end. And there they are stationary, so we can get a full reconstruction. But in the middle, we have very sparse data. And what we have is that very sparse data, which is sitting here in the middle. But we also have physical idea that the deformation of the velocity fields that the material points are going to be continuous in space and time. And we're going to use that idea of continuity in space and time to connect the beginning and the end with the sparse data set that we have in the middle. And that's what we basically do. We take that sparse data set and we do these neural reconstructions, basically. Okay, so how is it that what does it look like? So this is this thing. This is an architected solid. And what we are going to show you here is this architected solid deforming in 4.5 seconds. You see that this crush band forms in 3D in a very complex way. And the crush band typically is only is forming over 800 milliseconds. And we're going to show you how it is happening with a temporal resolution of approximately 100 milliseconds. So that's what you'll see here. So what you can see here is that we've basically managed to reconstruct this whole thing in a lab with a temporal resolution of 100 milliseconds in full 3D, basically. And we think we can go even faster. And this is, again, a combination of physics and sort of these data-driven methods that has allowed us to be able to do this kind of a reconstruction. Okay, so these first 2 points that I was talking about, they were sort of data-driven ideas, but they were basically at a very bird's eye view, really. I want to spend the rest of the sort of half an hour-ish that I have, basically, to talk about the third problem, where we are going to be doing digital image correlation, another technique. But I'm going to go into this a little bit more in depth. The reason I'm going to go a bit more in depth here is because, of course, the original idea here was a data-driven idea to collect data in 3D that we can then use to construct models, just like what we are trying to do for the metals. But what I want to show you here is actually the new physics that we are learning. Because in some ways, I don't want to only restrict ourselves to saying that we're just developing models, but the idea is you're also sort of learning new physics here. Okay, so now we'll go, as I said, a bit more in depth to remind you what, to people who don't know about this, is what is digital volume correlation. So if you want to do full 3D measurements of X-ray, which is essentially going to be using X-ray computed tomography and digital volume correlation together. So the idea is, of course, you have X-ray tomography where you take these, you keep rotating the specimen, get these projections, and then you do a reconstruction of the volume. Now, once you have reconstructed the volume, and you reconstruct the volume in the deformed or the undeformed and the deformed state, what you have here is that here you have this undeformed volume, here you have the deformed volume, and you basically are going to try to match how did a particular element, which I'm showing here by a cube, move from when it was within the undeformed volume, how did it move within the deformed volume. And if you can get hold of that mapping, of course, at that point, you've got hold of a strain field or a full displacement field, and you've got everything there. Now, to do that is not that straightforward. It's not that straightforward because how do you do this mapping from here to here? You need to have do some kind of correlation, which means you need to have some kind of microstructure to be able to actually correlate two images. Now, these are going to be three-dimensional images, but they're going to be three-dimensional volumes. How do you actually match them? You need to have some kind of a microstructure. Now, I'm going to take a material which has very little microstructure, which is silicon rubber. But when you look at it very carefully, you'll see that it does have a microstructure. So this is a piece of silicon rubber. And if you go deep into it, you'll see it has this kind of a microstructure. And this microstructure because it has essentially what we call a speckle pattern. And it's this speckle pattern that we will use to basically correlate one image to another image. And that's how we will be able to construct a displacement field in 3D. Okay, so what was the question? I remind you that the original question was to say it is data-driven. So we wanted to develop a model. We were not the first people to attempt this. But what I will say is that I wanted to see whether we can learn new physics in hyperelasticity. Well, that was not the original aim, but that's what ended up happening, basically. So to remind you, what is hyperelasticity? It's the most simple form of deformation, right? Robert Hooke was the person who basically came up with this idea 400-ish years ago. Is all that you have is this is a very simple material. You have something called an energy function, which we call a strain energy density function. It's a function only of the deformation, which I'm calling the deformation gradient, which is F. And if you know that function, W, some complex function of F, then the stress is given by just the gradient of that energy with respect to that deformation. So that's the very basic idea. So the only thing you have to do in this case, which is the simplest problem, is come up with this function W. Now, the bottom line is that many forms of this exist. The form of W, there's Ogden, Mooney-Rivlin, Aruda-Boyce. These are all the physical-based models that have existed for many years. This is the field where the field of data-driven mechanics essentially started. And many neural networks have been developed for describing W. As you can imagine, that's a relatively simple task. Of course, they've all used mainly synthetic data, not measured data. And we wanted to see whether we can do the same thing with real measurements rather than using synthetic data. And what you'll see is that we're going to end up with a problem, basically. Oops, sorry. OK, so let's go to the measurements. So very simple measurements. We take a cylinder of this material. We glue it to platens, as you can see here. And then we pull it in tension. And then you define sort of a stress-strain curve. It's not really stress-strain. It's sort of load displacement, because the strain that we're defining is just the displacement divided by the height of the specimen, and the stress is just the load divided by the cross-sectional area. Nothing at all remarkable, right? You basically get a curve that is nearly linear, a little bit of nonlinearity, and nearly no hysteresis. What you'd expect in a rubber, basically. Okay, so no surprises here at all, because these are very macro measurements. Let's go now to look at what does the field look like in 3D, because we have now done these measurements in 3D. Now, these are real measurements. These are not simulations. And so if you look at it, these are the sorts of volumetric fields that we are measuring. So what I'm talking to you here about is F33. What do I mean by F33? It is a deformation gradient in the actual direction that we are pulling this specimen. So what 1.25 here means is that it is 25% strain. And so what you're getting here is that you're getting less strain on the platens, near the platens, the top and the bottom, and more strain in the middle. That's not a surprise because of the gluing boundary conditions that was being used. If you look at a shear component of that of the deformation gradient, like a shear strain, well, you're getting something like that. You're seeing this sort of the sort of anti-symmetric pattern. This is red, blue here, like that. And that's because of the glued boundary condition. This specimen is wasting, and because of the wasting, you're getting that shear strain. So again, not a surprise. You've done all these very complex measurements, and you don't think you've learned anything dramatically new. So now let's see something which no two-dimensional measurement would have ever told you anything about. And what is that? One of the things that you can look, because we've got full 3D measurements, is we can look at the volumetric deformations point by point inside the specimen. Not the change in volume of the whole specimen, but each material point inside the specimen, how is its volume changing? So I'm now plotting here what we call the determinant of the deformation gradient, which in this case, what do I mean by that? It basically means that if the determinant is 1.1, that means I'm getting 10% increase in volume. If the determinant is 0.85, it means I'm getting a 15% reduction in the volume, basically. Okay, so that's what we are seeing here. So now let's look at this movie for a minute, and then we'll discuss what is the physics that it seems to be telling us. So if you look at this, you're going to see that it's something rather strange that has happened in the specimen. We have pulled the specimen in tension. And what has happened is that there is an outer shell that has formed where the deformation, where you're getting a 10% increase in volume, and an inner core where you're losing 15% in volume. So this is bizarre because you've pulled this in tension. Normally, if you pull it in tension, you either get a no volume change or you will get an increase in volume. But what we seem to have got is this mixture of volumetric gain and volumetric loss inside this rubber. But everybody would have told you that silicon rubber is an incompressible material, basically. How is this possible given this kind of measurement? Anyway, let's look at what happens over sort of deformation. This is 7% deformation, this is 14%, and this is that 21% overall deformation. So, this problem that we're getting seems to have evolved slowly as we increase the deformation. But as I said to you, everybody accepts that silicon rubber is an incompressible material. Well, if I then say that is this totally absurd, right? That I'm getting this mixture. Well, let's look at what's happened here. I'm now taking the volumetric average of this volumetric deformation over the whole specimen. So this angular bracket means average over the whole specimen. I'm getting numbers like 0.99, 0.98, 0.99. Well, that's within my error. And 1 means no volume in change, basically. So what it's telling you that over the whole specimen, this mixture of dilation and compaction seems to be canceling itself out, and the whole specimen is remaining incompressible. But at the local level, there is enormous compressibility in this specimen. So the literature, of course, was correct that silicon rubber at the specimen level is incompressible, but at the local level, at least these measurements are telling you it is highly compressible. So this is very strange behavior. And of course, this was one of the first new pieces of physics that we learned of. I will not go into the details of how many verification experiments we had to do to confirm that this is correct. Okay, so what is the problem? Is this strange behavior related to this specimen geometry, or is it something else that's happening here? So we made specimens of different sort of aspect ratios. This is a very long specimen. This is a shorter specimen. This is a shorter specimen. And this is that other the shortest specimen that you were seeing. And now what you can see, what's happening here, is this very long specimen was nearly incompressible in the middle. As you went shorter, well, you got more of this strange behavior. There's a little bit of green and a little bit of red. When you went shorter, now you're getting this blue and red, and then when you get even shorter, you get much more blue. So this problem seems to occur as you go shorter and shorter. Now, look at the length scale here. This is not some atomic length scale, right? This is 15 millimeters. So it seems as if at a very macro level, this specimen seems to see the boundaries, these glued boundaries that we had of the platons. Somehow or the other, this material is actually being able to see these boundaries, i.e. the gradients that are being created because of these boundaries. Okay, now if you agree that all these problems are occurring because of some boundary gradient effect, that the gradients of strain that are being created, then what else? How do you actually understand that? Right? You need to do a much more controlled experiment. So we do a 4-point bend experiment, which is the most controlled gradient experiment. So you do a 4-point bend test, you do this bending experiment like this, and now I'm plotting strains. Well, E11, which is the strain along the bending axis, well, you get tension here, compression here, as you expect. This is E22, which is you're getting compression at the top and tension at the bottom. This is the Poisson effect, exactly what you'd expect. This is the shear strain, E13. Well, it's nearly 0 in the middle, which is exactly what you'd expect for a 4-point bend experiment. But if you look at that volumetric strain again, which is now I'm plotting determinant of F minus 1, now you get really bizarre behavior. What you observe here is that on the compressive side out here, I'm seeing red. Basically, that means I've got a 10% volume increase here and approximately a 10% volume decrease on the tensile side. Now, this seems really bizarre. that I'm going to be able to get a 10% volume increase on the compressive side. And this is not some surface artifact. In fact, you can see that this was an internal section that we were showing you here because these were all from X-ray measurements. If you walk through the specimen, you get basically the same thing. It's pretty much all through the specimen. The same thing is happening. Now, it's clear that this is a problem. This is a problem because this would tell you that if you believed rubber elasticity, this is telling you that I'm going to get a negative bulk modulus, because we know that on the compressive side, the stresses have to be compressive, which means that if the volume is increasing, I'm getting negative, sort of a negative bulk modulus. And silicon rubber, we can hold it in our hands, we can play with it. It's a perfectly stable material. It doesn't have any negative moduli, basically. So there must be some other physics happening here which we have missed, which is what we now need to investigate. And so this is the sort of thing, right, what happened in this project. We started off with this project saying that we're going to get data by which we're going to develop these models, and then we realized that our starting assumptions of the physical assumptions you're making are wrong. So at this point, you have to start to hypothesize what are all the possibilities of the different kinds of physical ideas that are going wrong. Now, the first thing you realize when you sort of think about it from sort of a thermodynamic perspective, how can you get a negative bulk modulus? Well, you can't really get a negative bulk modulus. But the idea about a negative bulk modulus is only happening because you have said that the stress only depends on strain and nothing else. If you say to yourself that the stress depends on strain and some other internal variable, then thermodynamically something else is happening. So the question is there any possibility of another state variable effectively existing for this rubber rather than just strain? Now, you have to remember how you make silicon rubber. The way you make silicon rubber is you start with some sort of you basically take a polymer base and you add a catalyst into it. And that's how you basically start off a cross-linking reaction. And then you get yourself a rubber. Now, it is perfectly conceivable that that cross-linking was not complete. Is that you did not sort of complete the cross-linking when you added that catalyst. And what you'll have then remaining is something like this. Is you'll have lots of cross-linked molecules. And now what I'm showing by spheres, there won't be spheres basically. But you'll have some amount of number of molecules that will remain uncross-linked. And these will be mobile inside this whole cross-linked sort of medium basically. Now, if you have that kind of an idea, then this is what will happen. If you compress on one side, these uncross-linked molecules will move from one side to another side. And that's what you'll get a mobile species that are developing inside here. And that will give me this additional state variable that I'm looking for. Now, of course, we were investigating lots of different hypotheses, but this is the hypothesis that worked. So that's what I'm discussing, that this is the hypothesis that worked. Okay. So let's assume that this is the correct hypothesis, that you have a mobile species inside here. So can you actually prove that such a mobile species does exist inside this material? So can we actually directly see whether this mechanism holds? So you take, let's make another specimen. We take a beam. We basically make half of that beam where we take the silicon rubber, but we add a little bit of zinc iodide. Zinc iodide is an interesting thing because iodine is very X-ray opaque, so it acts as an X-ray marker. So it's going to act as a tracer, but it also sticks to silicon rubber molecules. So if this zinc iodide moves, I'll be able to see it inside by my X-ray method, basically. Okay, so if I look at this beam, and then this is what I've made up like this. I do this experiment. And this is what happened. What you can see is that all this black stuff which was sitting at the bottom has moved to the top, basically, the minute you do a compression experiment. When you do a tension experiment, you can see that it all remains on the same side, basically. It doesn't really move at all. So this has proved to us that there's something moving inside this material. And of course, this strange behavior remains that you're getting this flipping, effectively that you're getting the volume increasing on the side where this material is moving out from. Because what you can see here is that the material has moved from this compression side to the tension side. So volume is increasing on the compression side, and the volume is also decreasing. So how can you explain that? Well, effectively, the negative hydrostatic work must be sort of compensated by a positive sort of shear work or distortional work. Now, because I'm sort of being told I have only 10 minutes left, I'm going to speed up a little bit. What I'm going to say is that I'm going to sort of, you can develop a thermodynamic theory. And the thermodynamic theory means that now you've added one more state variable to the problem. In addition to strain, you've also added a concentration of this mobile species and the orientation of the mobile molecules. And you can now sort of run the handle of developing this kind of a theory. You have an elastic energy, you have a distortional energy. And you can define all these conjugates, etc., and you can solve this problem. So what happens when you actually solve this problem? So now that you've got yourself a consistent theory with this additional state variable, is if you look at what is it predicting, it's predicting exactly what we were observing. Is that on the compression side, the volume has increased, it's positive, and on the tension side, the volume has decreased, and the experiments and the simulations match. But the mobile phase concentration goes the opposite way, is that on the tension side, the mobile phase has increased, and on the compression side, the mobile phase has decreased. Very much like in what we were measuring. Okay, so this all seems to work out, but there's one problem that occurs. If something is moving, there has to be rate dependence in the problem, basically. How can something move and not have rate dependence? But I said to you that there's rubber. And actually speaking, there's very little evidence of rate dependence, negligible hysteresis. If you do a relaxation experiment, there's negligible relaxation. So there is no evidence in this case that over the rates that we are looking at, that you're getting any kind of rate dependence. So how is it that something is moving with no rate dependence? It would basically say that the diffusion rates of this mobile species inside this material are extremely fast. Crazily fast, in fact, 50 times faster than water in a hydrogel or something like that. Well, I can't, this is where I'm going to end, basically. I'm going to basically say I can't tell you why it's so fast, but I'm going to come back now to this idea about high-speed tomography and high-speed radiography. We actually looked at how fast it is moving. And when we did that, and this is what I'm going to show you, the last sort of experiment, is what's here is the blue. This is a 4-point bend experiment. The blue is air, the red is pure silicon rubber, the black down here has the zinc iodide, and the blue here again is. This whole thing is going to move up as we do this 4-point bend experiment. And what you will see here is that this black front moves nearly 5 millimeters in 4 seconds, basically. And it's moving so fast that is keeping up with the rate at which I'm deforming the specimen. And because it is keeping up with the rate at which I'm deforming the specimen, I am not observing any rate dependence in this problem, basically. Because at every step, this is essentially remaining in equilibrium because the diffusion is not occurring slow. Now, what is the process by which this diffusion is occurring so fast? I don't know. But this is this new physics that was being shown up. Okay, the last thing I'll say is that actually this thing exists in nearly all, at least we've been finding it exists in lots of materials which are made by some kind of a cross-linking reaction. This is 3-point bending of nylon, which is again a thermoplastic, engineering thermoplastic, and the same thing has occurred here. Is what you will see here is that you can see here that you're getting effectively compression on the bottom and volumetric gain on the top, basically, just like you were seeing for that silicon rubber. So this feature seems to be sort of relatively ubiquitous, at least for lots of different kinds of materials. Okay, so I'll end up by basically summarizing this, is that if you wanted to break this sort of traditional idea, which is how we started this, of a single material component, you needed to develop new optimization tools, measurement tools, data-driven tools, etc. And we started by developing those data-driven tools. But the interesting thing that came out from all those, we did develop those tools, but the interesting thing was not just that we had to develop data-driven methods, but it opened up new physics, basically, and which to me was very exciting, that these in the process of developing that, we are learning new physics. And what we basically have learned is that we can we can develop now new lab scale techniques for doing sort of 3D measurements, high X-ray fluxes, high sensitivity detectors, new reconstruction methods like those neural rendering methods. And we are democratizing synchrotron technologies. And I think this is really important because synchrotrons are, you can do very few experiments, really expensive, but if you can bring those techniques into a laboratory, that opens up a whole new bunch of science to be done, basically. So thank you very much.
We thank Professor DESHPANDE for the very fascinating and also very inspiring talk. My name is Zhongkin Su from Mechanical Engineering. I'm very happy to serve as a moderator for the discussion. Now we have approximately 30 minutes for the discussion. So now I would like to open the floor to invite any question. In both in this classroom and also online. So I would appreciate, so you begin with stating your name and also your academic unit, then we can know who you are. And in the meanwhile, I will also keep an eye on the online platform. So we may have some question from online audience rushing. Okay, so who wanted to be the first one? Oh, okay, the last row, yeah.
Good afternoon. Thank you very much for informative presentation. My name is Virag Raut, and I'm from Industrial Center. You mentioned about using X-rays to see the strain in the crystallites and all. Traditionally speaking, I mean, I used XRD, and we did use Williamson Hall plot method and the Scherer method to characterize the strains. So with this new method that you have proposed, did you sort of do any comparison from the traditional methods that can be strain can be extracted from purely X-ray data, and then now you have this new method, a setup with this method, you integrating machine learning, and then you are trying to get the strain data as well in the interstitial spaces and in the interatomic spaces.
Yes, thank you.
Thank you.
So just let's be clear, the XRD data, which we've got here, we've of course sort of, compared it and sort of verified it against the traditional XRD measurements, but they're giving elastic strains. And that's the key thing. While what we are now in the key thing in the new method is that we are basically being able to do elastic strains plus total strains. So we are basically being able to get the plastic deformations as well, basically. So of course, the way you truly can convince yourself that the XRD measurements are correct, that even in the plastic domain, remember that the XRD strains should still give you the elastic moduli, while the total strain measurements will sort of not give you the elastic moduli. And so that's effectively how we managed to compare, so sort of verify all of this.
Yeah, Huifeng.
Hey, Prof, we're from.
Yeah, no worry. You can start first.
Okay, sorry. Okay. My name is Ninghu Chang Hong, so a Presidential Center Professor from City University of Hong Kong, and my major is solid mechanics. In the past, I worked with Prof. Hua Jiangao. Thank you very much for your very interesting talk. And I have two questions I want to inquire and discuss with you. The first one is you showed that for the compression of the cellular structure, right? When you compress it fast or slow, it have different response, and then you use some machine learning or AI for reconstruction of the deformation, right, from the sparse data sheet. My question is, a lot of mechanical phenomena, especially for instability, they are, it happens really quickly, and there are some singular phenomena for those phenomena. How can we reconstruct?
Can you repeat your question? So a lot of these, you mentioned fast phenomena, but then I didn't understand.
Yeah, I mean, for those, when you compress, there are some instability, some snaps through, something like that. It happens very quick. mechanically or mathematically it's single node. So how can we reconstruct it from?
So you're saying, how can I go faster than I'm going right now, basically?
How can you reconstruct it?
Okay. So maybe I've not understood the question, but I'll try, and then you'll tell me whether I've understood your question. So right now we have made an assumption that the deformation, whether it's a snap through or whatever is happening here, is essentially a compatible event. So that means that the displacement of the velocity fields are continuous in space and time. This is not a fracture process or something like that, which would not be a discontinuous process. Now, once we have that, as long as we have this sparse data set, but we have this data where we have a projection at a different angle at a different time, that is sufficient. And, you can show that approximately mathematically is sufficient to, with that assumption of continuity, to do the reconstruction. Now, we have only done it at 100 milliseconds. I agree with you. And why are we restricted to 100 milliseconds? The reason we're restricted to 100 milliseconds is much like in high-speed photography. It's how many photons are you going to be able to get into your detector in a given amount of time. So if you want to go faster, you need a bigger flash in high-speed photography. Here we need a higher flux X-ray source. So we used a traditional low-flux tungsten X-ray source for those experiments. But if we used our metal jet X-ray source for those experiments, we would have been able to go much faster. So it's only a matter of flux of photons, basically, which will allow us to go faster. Just like in high-speed photography, you need a bigger flash.
Yeah. Okay. And following the second question, in fact, I think it's quite maybe a stupid question. In fact, currently all the measurement about force is indirectly. We measure the deformation, right? The displacement. Is it possible to measure the force directly? In fact, I have thought about this question for a long period of time.
Okay, so I will claim that a local force sensor is impossible. Effectively, we can talk about tractions, or I don't know what you mean by a local force sensor. But what has happened in the diffraction measurements? What has happened in the diffraction measurements is that we are measuring the changes in the atomic spacing. And when you measure the changes in the atomic spacing, this is exactly what would you do in a MD calculation, is when you define a virial stress or something like that. That's effectively what we have done, is we have basically said to ourselves that we know the changes in the atomic spacing. We know effectively the stiffness of the atomic bonds, which is the moduli, and that's how we can get the stress locally. So we convert the elastic strains, which are the changes in the atomic spacing, to stress via the moduli. But that is the one thing that we actually know pretty accurately for many alloys, because you can get hold of that from reasonably accurate potentials and things like that. It is the nonlinearity that occurs with plasticity, etc. That is the problem that these calculations are usually very bad at giving you. And that's why we feel that doing these measurements, where we make an assumption that we know the moduli, but we don't know the nonlinear behavior, is okay, basically.
Okay. I still have a lot of questions, but I think I need to give other people opportunities.
Okay. Yeah, Huipeng, follow up. Yes.
Well, thank you for the interesting talk, Professor Deshpande. I just have one question regarding, my name is Huifeng Du from Mechanical Engineering, by the way. And I just have one quick question about the rubber elasticity. So you went through the last bit of modeling pretty fast, but is it possible to introduce some kind of intrinsic length scale in your modeling? And do you expect the traditional assumption of the rubber's incompressibility to be recovered maybe at a smaller scale? Can you comment on that? Yeah.
Yes, that's a very interesting question. That was, of course, one of our first hypotheses, that you have some sort of intrinsic length scale, i.e. gradients of strain, matter, etc. Now, the minute you do that, you'll get a size dependence of the problem. And in the paper that I cited there, we did experiments at different length scales, and we showed there is no size dependence of the problem. And that is how we proved that there is no intrinsic length scale. That hypothesis doesn't work.
Oh, it'd be interesting to see your future work, to see maybe you go down to the molecular scale, and maybe that's a new physics emerge at that.
Sorry, could you repeat? I missed your.
So maybe if you go down to the molecular level, maybe at the polymer chains length scale, would there be like new physics emerge?
Most probably you're correct.
Huh?
The only thing which I'll say is that I would claim the key physics is this, that fact that some of these chains are mobile. And I feel that we've proven that by those zinc iodide experiments where we showed that the thing was moving, basically. Is most rubber theories, a lot of calculations have been done on sort of understanding the relationship between the chain or the entanglement and rubber elasticity. They don't assume a mobile phase. That physics has not yet been incorporated mainly because I think people thought it doesn't happen, basically.
Yeah. Well, thank you. It's also be interesting to benchmark against a really incompressible material in the future, like hydrogel, like see how that behaves differently with your like rubber.
So no. So actually, there's enormous similarities between this and hydrogels because hydrogels also have a mobile phase in them.
Okay. Yeah.
The only difference is this fact, which I went through too quickly, I must admit, is how come when you get compressive hydrostatic stresses, you get dilation, which will not happen in a hydrogel. And that comes because we are saying that the mobile phase is generating distortional work in addition to just volumetric work. So that's the one difference between a hydrogel and this, basically.
All right. Thank you.
Yeah, Professor Chen.
Thank you, Vikram, for this very interesting talk. So it's amazing to see how actually from measurements you dig out so much physics, which in my opinion is of fundamental importance. Now, I'm interested in the phenomena that you mentioned, this cross-linking mechanism. So I'm wondering, is there any attempt to make use of this phenomena to design not only new materials, but also new structures? Because nowadays the manufacturing capability is increasing. And then we see a lot of examples of, metal materials, engineered materials like lattice or whatever. Is there any room, or are you?
Without any question, this, Professor Cheng, this is, I didn't go into all the details here. Is you can change the amount of cross-linking, you can change the amount of this mobile phase, and we showed that in the paper. But what we haven't done yet, but it's an obvious next step, is to put magnetic particles or other things, and these will move just like the zinc iodide particles are moving. And that means that these will become intrinsic sensors. So if you want to do sort of, you have this rubber, but it could also become an intrinsic sensor because you'll be able to measure the changes in the magnetic fields or maybe electric fields, etc. I'm not saying I know exactly how to do all this, but these are clear things where you can start thinking of how to use this physics, basically.
Especially with your system in place, okay, it's possible to monitor, okay, the way you manipulate, okay.
That's right. I think that, for structural health monitoring, et cetera, right? Because, you'll be able to do non-contact sensing, et cetera, because if you have magnetic fields, et cetera, that you can measure. Right.
Okay, thank you.
Okay, yeah, actually a lot of questions already rush in from our online audience. Let me pick up the first 2 or 3. Yeah, so we got a long list, just like we promised during lunchtime. We tried to make you feel you were attending a PhD defense.
I hope I don't fail it.
Yeah, the first question. So how would AI help the data-driven mechanics?
Okay, so now this is, my answer is going to be controversial, just because it's fun. So one of the things which I will say is there's one place in mechanics where data-driven AI is going to be extremely useful. And this, for example, I gave this high-speed reconstruction, this neural rendering reconstruction. This was inconceivable with current hardware systems or with the sort of traditional reconstruction method. This only happened because of these new AI methods where we can do sort of, discovery or, do these kinds of things with sparse data sets. So a lot of mechanics has images in it, and images are extremely expensive, difficult to obtain. And I think that AI is going to have huge influence in this field, basically. Whether AI is going to have a big influence in fields where actually we know the physics reasonably well already, like plasticity theory. Why did I not talk about those neural network models of plasticity more? Is actually speaking, the physics there is so well known, it is unclear whether AI will have a big impact. It may have an impact in this business where you want to do autonomous, going from data measurement to model generation in an autonomous manner. If that is the case, then of course these AI methods are going to be useful. But I don't think they will be better than the existing models. But they will add this autonomy to it, if that is the interest, basically.
Yeah. Okay. Another question from someone asked, so when you have the measurement strategy, so they can make a lot of improvement to the data-driven mechanics. Do you think what is most important improvement of the new measurement strategy in data-driven mechanics?
So this is a very tricky question, actually. And this is the difference between data and information. Actually speaking, we can collect lots of data, but you're not adding information. And let me give you the example. Suppose I do pure DIC measurements and I keep increasing the resolution of my DIC measurement. I'll get more and more data from it, but actually I will not add much more information. What is needed in lots of these data-driven methods is new information rather than just new data. The word data is used badly. So what you need to do is you need to come up with methods that add new information. So this is why we said we did digital image correlation, which gave one sort of data. Then we did XRD, or diffraction, which gives us completely different orthogonal data, which gives us new information. And so this is, I think, what we should be always talking about, getting new information rather than just getting more data.
Okay. Probably I can take the advantage to ask one question. So traditionally, we have the so-called physics-based mechanics. So that is, we feel very confident. So if we can analytically, theoretically, or even semi-analytically to model something and try to understand the underlying physics of any mechanics phenomenon. Now today we have the so-called the measurement data driven mechanics. So I trust you agree with me. So neither can survive independently. That's because today's mechanics phenomena too is complicated, very difficult to get the pure analytical solution. Well, on another hand, so experiment too expensive. You cannot fully based on the data. So do you think there is some optimal balance point? So that is between the data-driven mechanics and the physics-driven mechanics?
It has to be attained. I'm not saying I know how to attain that balance. For example, in the rubber problem, I will claim that we attempted to do that balance. We said that we will assume that this is a hyperelastic material. So we constrained the physics to be hyperelasticity. And then we found we couldn't fit any of the machine learning model or AI models to that data set. And that's because the underlying physical assumptions that had gone in were wrong, basically. So we were trying to do that. And then, of course, we had to do more experimentation to understand where is the physics. And now, of course, we can do a data-driven model. So essentially, it's going to be an iterative process, because if you have made wrong physical assumptions and you've constrained your data-driven model to be that physics, but that physics is fundamentally wrong, then it's never going to work. And I don't think that we'll ever come up with and the other approach, which is pure data-driven, which some people claim. But as an experimentalist, I'll tell you this, we'll never be able to get, at least in the near future, collect enough data that we will be able to purely do a data-driven model with no physics. There has to be some kind of an iterative process, is what I'll claim.
Yeah. One follow-up question is, so when you do the measurement data, when you get the measurement data-driven mechanics, when you do the modeling, so that is based on something already existed there. So you do you have the loading, you have the structure, everything is fixed. Then you do the testing. Then later on, when you develop the model, what you want to do is to predict something new, never happened. So here, probably some implication is what is the trust or the confidence or the reliability when you extend using the existing data to predict something new?
So we do. So I went a bit too quickly. So in that neural network plasticity model that we developed using that XRD idea, is we had calibrated the neural network model with using a simple notch specimen. But then we validated that model on these much more complex geometries. And we validate against a series of those complex geometry. So this is traditional in any sort of machine learning AI method, is that you use some amount of your data for training of your model and some amount of it for validation. So I think that idea basically still works. Of course, the key is going to be the design of the validation tests, basically. But I think this is where our physical insights come in really usefully, is that how do you design those validation tests, basically.
Okay, thank you. One more question from online. So what research scenarios and the data types these measurement strategies mainly applied to?
What data type?
Like talking about some application scenarios.
Okay, so I think the simplest application is to give you what we were trying to do, which is this multi-material BLISC. That was our model test problem. Is that we wanted to say that we have data on 150 alloys, and then we can now that we have the 150 alloys, we can then use it in an optimization framework to generate a multi-material structural design. So this was one specific case where we really needed the autonomous idea, but going from measurement to model in an autonomous way, because we are not going to sit and generate models in 150 manually. So this is the one example. I think people can come up with, especially in alloy design, this is one of the main things, is that as you're doing, these new additive methods are coming up where people can make lots of different alloys, is you need an autonomous way to be able to generate the properties of these alloys. And this is another place where these data-driven methods will come in.
Hello, Vikram. Thank you very much for your very impressive talk. And my name is Lei Yang from ME department. And it's very good to see some familiar names on your slides. And I actually have two questions. And the first question is like, when you introduce the in-situ diagnostics for the measurements, and most of them are from causes stick or low speed loading, right?
Yeah.
Do you have any ideas like how can we measure some quantitative information or in-situ diagnostics for the very high-speed experiments, such as in a microsecond scale?
At the, sorry, what scale?
Microsecond scale.
Okay, so effectively, this second part of my talk, which was on talking about 4D tomography, and I'm not talking about diffraction, etc. At that point, I'm talking only of 3D visualization. We think that I agree with you that I've only shown it to you at 100 millisecond timescales at the moment, but we've already gone down to 1 millisecond, and we think we know how to do it even at microsecond timescales. And as I said to you, the constraint right now is purely based upon photon flux, some other practical constraints as well. But photon flux is not really a constraint for the notion of flash X-rays have existed for maybe 50 years, basically. So flash X-rays, if you have flash X-rays in your lab, which at least the big defense labs definitely have them, but they have been using it only for tomography, for radiography at the moment. But with flash X-rays, we can now do high-speed microsecond tomography. But with this idea about bringing in these AI tools, basically, that you can use reconstruction from sparse data sets. So I don't think that the day is very far off where we'll be able to do 4D reconstruction at microsecond timescales in a lab.
Okay, thank you. So actually, I have some experience by using the infrared X-ray to measure the deformation, to measure internal deformation of the porous material. But for the very dense material, I think even though in-situ fresh X-ray cannot get somewhere useful.
No, I agree. With very dense materials, I agree with you that if some people, especially for these modern applications for fusion and nuclear reactors, they talk of tungsten and things like that as being the materials. Once you go to those extremely dense materials, then I agree with you. At the moment, at least, I don't have ideas of how to do that.
So just ask a following question. So, do you have any ideas how can we integrate the high throughput facilities in the lab with your X-ray or XRD? How can we integrate the high throughput facilities with the X-ray or XRD in the laboratory?
So that sort of, I didn't discuss this, but this is where I think having these neural network models, basically, effectively having this autonomous workflows. And this actually is not that difficult, is that we're going straight from effectively all that facility that I showed you, where we're doing these XRD DIC measurements and developing neural network models. They're pretty autonomous. Is that you go from data to to getting to the level of a full neural network model for plasticity. That it's pretty autonomous. The biggest issue there, and this is why it's not used at them, is they can go wrong. These workflows can go, the human intervention, what it does is that when you have noise in the data, it understands that this is bad data, and you can, it removes. These purely autonomous workflow sort of things that we have done so far are not smart enough to basically not realize that, something has gone wrong in the experiment, and, this data should be thrown away, or at least some parts of that data should be thrown away. So this is the bottleneck, but I don't see how that is going to be not solved. These AI tools, in principle, should be able to be improved to be able to deal with such problems.
Okay, thank you. That's my question.
Yeah, here's one more question. So because data-driven mechanics must be fully rely on the intensive experiment.
Yeah.
Yeah, so here one question is the data standard or reproducibility must be very, very critical, because you need to repeat a lot of experiment. So do you have any comments?
Okay. So now there are two ways you can get a lot of data, and I didn't make that clear. One is you can do lots of experiments. What we took another approach. We said we do one experiment, but we get a lot of data from that one experiment. So there are these two approaches. And again, as the field moves forward, I think it'll be a combination of the two ideas that work, basically. But this idea about reproducibility and sort of understanding whether the data that you're collecting has problems in it is critical. And I'm not claiming that has been solved. And that was related to the previous question, is in developing these autonomous workflows, is we need a protocol to realize that, some data, either some experiment or some data point that I've measured needs to be thrown out from the data set because something had gone wrong there. And those kinds of tools have not yet been developed sufficiently.
Yeah. Professor Yu. Use a microphone. Okay.
Learn a lot. And my question is that for some non-metal materials such as silicon rubber or nylon, it may have a viscosity. So I just wondering whether your new measurement strategy can including the viscosity in addition to the elasticity and the plasticity.
Yeah, very good question, Professor Yu. So this is partly why we wanted to develop a higher speed, I would not even call it high speed, higher speed tomography system, basically. If you want to measure, say, viscosity, think of a normal composite whose matrix has relaxation times on the order of a few minutes, basically. Is if you can develop these, this is what the aim was of those measurement methods where we did, the so-called high-speed tomography or 4D measurements, is now we can do tomography definitely with interframe times of, few seconds. And that means we can now start looking at viscoelasticity and other kinds of material phenomena. We have started looking at it very much so right now, using those kinds of ideas.
Yeah, so here's one more question that is to some degree related to Professor Cheng's question. So that is much of today's engineering design still pretty much based on the relatively simple material parameter yielding stress, fracture toughness, SN curve or something, very easy to be implemented in engineering practice. So how do you envision in future how your advanced measurement strategies eventually will fit the engineering practice?
So actually speaking, if you solve these problems about data reliability, which we haven't, I must admit that.
Reliability.
Yeah, reliability. Actually, that is actually why these things will be implemented in engineering practice much easier. And I'll give you the example. So once you develop these neural network models, they are totally generic. They will not care whether they're plasticity models, fatigue models, or those kinds of models. And for example, we've already implemented some of these neural network models in sort of softwares like Moose. Moose is a very generic piece of software developed by Idaho National Labs. And so these neural networks already exist. So all that you need to do is when you train your new model, this just becomes a new parameter set in Moose, basically. So that part actually is why they are so attractive. I mean, for a person like me, I say, actually, I much prefer the physics-based model. But every physics-based model needs to be recoded into one of these codes. But that is not true for these neural network models. And so that is one of the big advantages.
Yeah, okay. So the last question, so probably we have only 2 minutes to accommodate the last question. Yeah, please.
Yeah.
Okay, Prof. Vikram. My last question is, I'm getting puzzling about, if driven mechanics or AI, it seems that they are very powerful. They can solve most of the existing mechanics problems. Then for those young researchers on mechanics, should we devote so much energy for the development of new models, physical models or mechanics models, or should are there any space or less necessity to do that kind of work, or should we focus more on maybe new paradigm?
So the first thing I'll say is what I was saying earlier, to Professor Su's comment, is materials will, for the foreseeable future, will remain a data poor field, how much ever we are improving our data, which means that without some combination of physics-based models and data-driven models, a pure data-driven model, I do not foresee in the near future it being possible, because we just will not have enough data, unlike in certain other fields where data is relatively cheap. So we will always we'll have some combination of a physics-based model and a data-driven model. Even our data-driven models have a lot of physics included in them. I don't like to use the word physics-informed neural networks, but they effectively, all of them are. We never have enough data to be purely data-driven at the moment.
Okay. Yeah, actually, we still have a long list of the questions, but colleagues already reminded several times, so we already used that all the time.
I apologize if I took more time than I should for my talk.
Sure, no worries. Yeah, I'll pass the stage to.
Thank you.
Oh, yes, another round of applause. So to express our appreciation to your wonderful lecture, we make this special plaque for you with your name and lecture titles, etc.
Thank you very much.
Now I would like also invite Professor Su, Professor Chen, and also Professor Key all together to take another photo.
Thank you very much.
All right, yeah, thank you very much. And I'd also I'd like to thank all of you for coming here today. You know that the pair organizes the distinguished lectures from time to time. So just please pay attention to our announcement, and we'll welcome you back. So I'd like to thank all of you for your participation, especially for those who ask questions. Thank you very much. So this lecture is adjourned.